Alright, welcome to an introduction to partial fraction decomposition. This is in preparation for actually integrating by partial fraction decomposition. So in Calculus 2, we could be asked to integrate things such as x plus 5 divided by x plus 1 times x plus 3. And using techniques we already know, such as U substitution, we actually aren't able to tackle this integral. What partial fraction decomposition does is it breaks the integrand up into a sum or difference of smaller fractions that we should be able to tackle. So it's actually really just going to be an algebra process to actually decompose the fractions, and then it helps us out in the context of calculus. So what I'd like to do is not overwhelm you with cases, but show you that there are 4 cases that partial fraction decomposition could fall into. And we'll look at an example of each case in terms of just structure, and then we'll try to work through at least one of these. So the first case, if you focus just on the first case here, means that we have the denominator of the fraction being a product of distinct linear factors. So in this example, you can see here that x plus 1 is a linear factor, and that's being multiplied by another linear factor. So that's the first case. The second case is very similar to the first case in that we're looking at a product of linear factors. So in a sense, case 1 and case 2 very much go hand in hand. The only difference is that case 2 allows for some of those factors to be repeated. So you can see that the original denominator in this example has x squared, which we view as really x times x, right? So it's the product of linear factors still. And then we have the x minus 1, again a linear factor, but it's being cubed, so that's another repeated factor. Case 2 is kind of interesting because we have to build up to the actual term. So this x squared term, we build up to it by starting with a denominator of x and then x squared. In a similar fashion, to get the x minus 1 cubed, we have to do an x minus 1 to the first, an x minus 1 squared, and then an x minus 1 cubed term. And you'll notice that the numerators in these examples are just unknowns, right? So essentially our algebra process would be solving for these values a, b, c, d, and e in hopes that then our calculus skills would allow us to integrate the resulting pieces. So it takes a little bit of getting used to. Just real quick to look at cases 3 and 4. Case 1 and case 2 are very common. Case 3 is pretty common. Case 4, not as much. I mean, just in the context of practicing for Calc 2. But case 3 and 4 go hand in hand in that they are going to be products of quadratic factors. So case 1 and 2 is all about linear factors. And then cases 3 and 4 will be about quadratic factors that can't be reduced. So what we mean by that is x squared plus 1, for example. That is a quadratic factor because it has an x squared term. It's not reducible because x squared plus 1 doesn't factor, right? That's basically prime. And the way we handle these quadratic factors is we have to make the numerator 1 degree less than the quadratic factor. So, for example, when I have this x squared plus 1 denominator, the numerator is bx plus c. Now b and c are values we'll be solving for, but notice that bx plus c is linear, so it's 1 degree less than the quadratic term. In the same example, you'll notice we had an x minus 2 term. That term is linear, so 1 degree less than a linear term is just a constant term. And last but not least, this x squared plus 4 is another quadratic irreducible factor. Therefore, the numerator on that piece would be a linear factor. And case 4, I won't bother saying too much for the moment, but the only difference is case 4 allows for repeated irreducible quadratic factors. Alright, so that was a mouthful. Don't be overwhelmed. We'll just work through this kind of case by case. I'd like to work fully through a case 1 example, and then that might be it for our time here today. But this is case 1, product of distinct linear factors. And the way it's broken up is it will then be the sum of some value divided by x plus 1 plus some value divided by x plus 3. So our goal right now algebraically is to solve for a and b. What we can start by doing is getting each fraction to have the same common denominator, which is of course the x plus 1 times the x plus 3 term on the left side of the equation. So I'm just going to show changing each fraction to have that LCD. So the first fraction, which has the x plus 1 denominator, we can tell that fraction is in need of the factor of x plus 3. We'll just introduce what it's missing, top and bottom, so that it shares the denominator of the term on the left. The second fraction on the right-hand side has the factor of x plus 3, so it needs the factor of x plus 1. So at this point, we can see that all the denominators in the equation are the same. Therefore, if we multiply through by the LCD, that will essentially wipe out all the denominators. And for the sake of space, I am just going to cross out all those denominators. So we are left with now x plus 5 is equal to a times x plus 3 plus b times x plus 1. There are a couple different strategies that can be used to solve from here on out. What I'm going to introduce first is choosing strategic values of x in order to solve for a and b. So what I mean by that is, let's say I wanted to solve for b. I notice that if I choose an x value of -3, my a term is going to disappear altogether, because popping in a -3 right here and then adding it with 3 would be 0. 0 times a would just be 0. So let's try evaluating the equation at an x value of -3. Again, that's our strategic choice because it will wipe out the a term, allowing us to solve for the b term. So the left-hand side, if I plug in a -3 right here, would give -3 plus 5, or just 2. On the right-hand side, the whole a term wipes out, as we discussed. Plugging in -3 right here gives us -3 plus 1, which is -2. So we have -2 times b. So that dramatically simplifies the equation. It also allows us to see very readily that if 2 is equal to -2b, b must have the value of -1. So far we found the value of b. If we use this same technique again, we can find the value of a. So what value of x do you think we would want to plug in to get rid of the b term and then find the a term? Think about that for just a brief moment, and I'll get some more space here. We're trying to figure out what would wipe out the b term and allow us to solve for a. So focusing on this x value right here, if we plug in -1, we would then be adding 1, which of course would be 0, timesing by b is 0. So let's plug in an x value of -1. On the left side of the equation, -1 plus 5 would give us just 4. On the right, -1 plus 3 is 2. That's being times by a. And again, this whole term right here, the b times x plus 1, zeroes out. So if 4 is equal to 2a, that helps us see that a must just have a value of 2. So this is rather exciting because what we now can say is the original fraction of x plus 5 divided by x plus 1 times x plus 3 can be rewritten as a over x plus 1, and a was again just 2, added with b over x plus 3, and we just found b has a value of -1. So maybe I'll just go ahead and say, instead of plus -1, we'll just say -1 over x plus 3. And again, keeping the context of calculus in mind, this is rather exciting as well because we would know how to integrate this term, the 2 over x plus 1. We could integrate that with what we know about natural log. Similarly, we would have no trouble integrating negative 1 over x plus 3. So that is, again, just a case 1 example. The other cases, which we looked at briefly, will be addressed at a later time. But the good news is it's primarily algebra. So try out some practice, and we'll see you very soon in Calculus 2.